All right, welcome back. Today is October the 5th, and we're going to finish up the worksheet or practice homework number 6. All right, the last time we were working on it, we stopped here on problem number 2, and we were comparing oxymercuration to hydroboration to hydration, and we were comparing the final products. And so we noticed that for oxymercuration, we know that there are no carbocation rearrangements. So even if there's a tertiary the potential for a tertiary carbocation, it will not form it because you have a locked configuration with the mercurinium ion. And so usually it will give you a secondary alcohol. For the hydroboration, the OH always goes to the least substituted carbon. That's why it's considered in an anti-Markovnikov reaction. And then for hydration, for hydroboration also there's no carbocation rearrangement. And for hydration, we do get a Markovnikov addition and carbocation rearrangements, and the molecule will rearrange until it gets the most stable carbocation, usually tertiary, and so the OH will go to the most substituted carbon right there. All right, so we're gonna finish this worksheet, and I'll give you an extra one in case we need some more material. Hopefully you guys had a chance to get it. I sent it last night around 9:10 or something. So let's finish this up. Okay, so what do we have here? We have an alkene. We have an intermediate that has a mercury atom, so that's oxymercuration immediately. And then notice that this mercury group turns into hydrogen. And so that's from the addition of sodium borohydride is adding a hydride. So this is going to be also a case of oxymercuration, demercuration. All right. And there's 2 hydrogens here. There's also one here to start. That's why I was only saying that we put a hydride there. You need to write it down. It's implied that a carbon like that is a CH2. Now you are advanced for this. So this reaction does undergo Markovnikov addition. All right, so what would be the ingredients for this part here? That's what I'm looking for. How do you figure that out? So you look at this, the mercury acetate group, and you look at this. What is this? Where did that come from? The one on the top, the alkoxide. Anybody? Can you give me the ingredients for this reaction? The reagents. I got 37 participants. Come on. Yes, ma'am.
Is it HgOAC2 on the top and then H2O and Et2O on the bottom?
Okay, hold on. Let me write this down first. Very good, Hannah. So you say that, right? And so
yes.
what would be the second part?
On the bottom it's H2O
No, it won't be
Oh.
H2O. If it was H2O, we'll get this. You see the difference?
Mm-hmm.
So we're adding an alcohol. What's the alcohol that I need? What does this look like to you? What is the name of this alcohol? What is that alcohol?
Is it phenol?
No. Close. What else? Read this. What is this?
Is it isopropyl alcohol?
Yes, isopropyl alcohol, also known as 2-propanol, also known as rubbing alcohol. Yeah, so that's what we need, because that is that. Okay. Remember that the acetate group steals this H, so that's why you end up with just the alkoxide. All right, very good. What about the last problem here? First of all, is this Markovnikov, anti-Markovnikov event, or neither? You think? And give me the name of this reaction. What is happening? So here I have an alkene, and I'm adding two hydrogens. Two hydrogens. That looks like hydrogen gas. All right. So this is gonna be hydrogen gas. What else do I need to make this happen? What is that? What is happening in there? Anybody? It's important if you participate, because I have the answers. I want to see if you know this. Who can answer this question before we kill too much time?
Does it have to do with breaking that double bond?
Yes, we're breaking the double bond and we're adding hydrogens to it. What is the name of that reaction? And what does it need? It needs something else here. If you have a flask with, and you fill it with an alkene, and you add hydrogen gas to it, and you cover it, you cap it really tight, this will form this. This will form the cycloalkane in 1,000,000 years. It'll take 1,000,000 years to get that reaction going. But if we catalyze this reaction, we can get it in an hour. How cool is that? So what do I need here?
Is it P?
Huh?
P?
Heat?
Platinum?
Platinum, yes. I need a catalyst. Platinum, palladium, or nickel will work here. I like platinum. It's expensive. It's an expensive reagent. Likewise, palladium too. These are very precious metals. And so what we do in the lab, when we buy these precious metals, we recycle them. We put them in a small jar where we can properly dispose them. And people can purify the platinum again and reuse them, because it took a lot of money to make it from a mine, to extract it. And so we use it in very small amounts, but we still recycle them. So yeah, so if you add platinum to this reaction, we make this in 1 hour. All right. If this is a Markovnikov or anti-Markovnikov, or neither.
Neither.
Neither, exactly. We are, so what the double bond does is that, according to the mechanism, is if this is a piece of platinum, hydrogen will bind to the metal, and then each hydrogen will go to the carbons on the alkene, making this. And so this is a syn addition, which means that it happens on the same face of the double bond. Could be up or down. In this case, it doesn't matter. This molecule is symmetrical. See, there's a plane of symmetry there. So whether these metals are up or down is the same thing. You just flip the molecule, it's the same thing. So the name of this reaction is catalytic hydrogenation, or simply hydrogenation. All right, very good. Let's do problem 3. Predict the final products from the following reaction. Whenever enantiomers can be formed, draw them. All right, so this might be hard for you to explain with your own words. So what I'm gonna ask here is, how many final products will I make from this reaction? 1 or 2? Come on, give me a number. 1 or 2?
1.
It'll be 2. So here's why. So you will make 2 possible intermediates. You make this one, this is your bromonium ion, and you also make another one that it's enantiomer. So where it's gonna be facing down. All right, and you have bromine minus here waiting to do the attacks. All right, the bromine, where would the bromine attack? Your options are carbon number 1 or carbon number 2.
Is it carbon number 1 because the bond is longer and easier to break?
Yes, exactly right. Carbon number 1 is the choice. So this is gonna go attached. Oh, hold on a second. I think I erased this bond here. So this had to come from the top. Let me get a different color pen. So when it does that, it breaks this bond right here, and it pushes the ethyl group up. And then for this one, it does the same thing. So let's call this A. Wait. And path B. So we're gonna make 2 products for A, I get, so notice that this is going to be the attack needs, this one comes from the bottom, right? Because it's an anti-attack, has to be opposite to where the breakage it's gonna happen. So the breakage is here, and this one will break right here. Okay, so this attack, the left attack is on the bottom, and the other one is from the top. And so,
why would you consider that on the bottom? Why would you consider A attacking on the bottom?
Because the attack on A has to be opposite to these bonds. So these bonds right here for the bromonium ion are up. You see them now?
Yes.
So it had to be opposite to that. It's an anti-addition. So A, product for A, product for B will look like this. For A, I will have this bromine will be up. It stays up. What's happened to the ethyl group? The ethyl group is going to be up also, right? Because it gets pushed. And the new bromine goes on the bottom. The other one will be for B. This bromine stays down. The ethyl group gets pushed down now, and the new bromine is gonna be up. All right, that's what you get there. Make sure you practice this. All right, notice that I took the same molecule and just rotated it. Here I rotated it counterclockwise and then counterclockwise. That is the same thing. So you get, why do I do this? So you get used to seeing the molecules under different perspectives, but it's still the same thing. All right, so the next question, oh, what's the name of this reaction? Anybody? Start with an H. All these reactions start with an H, pretty much.
Is that halogenation?
Yes, halogenation. How about the next one? What's the name of that reaction to start?
Halohydrin.
Halohydrin, yes. How do I remember this? This is easier. If it's bromine, I know B. Oh, that reminds me of Beyonce, and Halo reminds me of that song Halo that she sings. So the problem is, if it's chlorine, then I'm stuck. I don't know who to assign to, but still, you know, that's the halohydrin.
Is that always water with it?
Yeah, halohydrin will always have water or an alcohol. All right. So you will have this same, the same intermediates, those two. All right. Same exact intermediates here. I'm not gonna draw them to save some time. And then we're gonna have two attacks, one from the top and one from the bottom. Same thing. So which one will be A? A will be the bottom attack, and B will be the top attack. So A will now be, check this out. I'm gonna put it this way. and bromine will be up, the ethyl will be up, the bromine will be up, and my OH will be down. Notice that that's your nucleophile. Here was your nucleophile. We just rotated this molecule 100, maybe 90 degrees counterclockwise. The next is the ethyl will be down, the bromine that was on the ring will be down, and the new nucleophile will be up. How super duper cool is that? All right, let's do the third one. What is this? What's the name for that? What is that? The generic name of this reagent. It's a pair acid, right? So what does pair acids do? They do oxidations. All right. So how many products will you get here? Because this molecule is not symmetrical, it's not. How many you will get?
Would it just be one?
It'll be two. But thank you for participating, because to me that's more important than being right. All right, so I'm gonna set this up. Check this out. I'm gonna make an epoxide that is up. And the ethyl will be down on this one. For this one, on the right side, the epoxide, this epoxide is symmetrical. But this one will be up, the ethyl will be up. So we get two products, and those are enantiomers. Yes, they are. How do I know? I'm gonna take, if you were to rotate this molecule, let's rotate them so you can see it. I'm gonna rotate the one on the right, on the left, 180 degrees facing this way. And I'm gonna put my mirror image right here. And so the one on the right, I'm gonna flip it vertically 180 degrees. You see that? I'm gonna flip this, and soon you will see that now the epoxy group is up, and the ethyl group will end up here down. You see it? So these are enantiomers. All right. What's the name of the next reaction? Anybody?
Is it ozonolysis?
No, that's not ozonolysis. Ozonolysis, the one that is after that. But
dihydroxylation.
Yes. Dihydroxylation. This would have been good for a second try or second attempt. Not bad. So also notice that these are under reductive workup conditions. So we're not gonna open any double bonds. All right. So how many products do you expect? Is it one or two? This is the same molecule as those three. Just rotate it one more time. So you get 2. Let's put this in green. So I put my 2 skeletons here, carbon skeletons. And so the double bond here, first it's gonna be dihydroxylated with 2 OHs up. That means this ethyl group will be pushed down. For the other one, start with the hydroxides, put them both down, then make your ethyl group go up. And that's it. Last one. I'm gonna rotate this one more time and flip it this time. It's the same molecule. How many products do I expect here? And by the way, what is the name of this reaction? What is the name of this reaction?
Ozonolysis.
Yes, ozonolysis. All right. What happened in ozonolysis? To me, this is the one time the bully. Here's your bully. The alkene is the bully because it's electron rich. Since the poor ozone here, ozone is the electron plus. And then ozone sees the alkene come. He knows he's gonna get hurt. But he tells him, I know you're gonna beat me. But before you beat me, I'm gonna break you in half. Before I'm completely destroyed, at least I will break you. It says that. So, and when that happens, you put in there and an oxygen here. Let me see. This is kind of too close. Let me make it bigger. So the breakage happens here, and then here there will be an oxygen, and there will be another oxygen put in place there, and now you made 2 carbonyl groups. That's what ozone does to the alkene. All right, so this is what I would do if I was you. I count the carbons around the ring only. So 1, 2, 3, 4, 5, and 6. So I have 6 carbons. All right. Wait. Yeah. Zoom is low. All right. I'm gonna do 6 carbons. 1, 2. And how many probes am I gonna get? 1. 1, 2, 3, 4, 5, and 6. So this is carbons 1, 2. Oh, I want a different color. Oh, this delay in erasing is so annoying. Look, I'm actually erasing everything and it doesn't do it. All right, let's redo this. 1, 2, 3, 4, 3, 4, 5, and 6. All right, and I'm gonna label it 1, 2, 3, 4, 5, and 6. So what happened on 5? On 1. On 1, I make a carbonyl group. And on 6, no, that's not true. That is not true. On 1, hold on a second. So this is carbon 1. So if I go 1, I need to count this around opposite. Let me check this out so that the counting works. I need to say 1, 2, 3, 4, 5, and 6. Now that will work because I will have carbonyls on both ends. So on carbon 1, I have an ethyl group, and on carbon 6, I have a hydrogen. So I just put a hydrogen there. All right, so that's how you solve for that ozonolysis. Any questions to this point? Notice that this is under reduction workup, and that aldehyde stays. You have an aldehyde and a ketone. Ketone is at 1. If you had oxidative workup conditions, you end up with a carboxylic acid, so you will have to insert an oxygen right there. Oxygen insertion will be the final product if hydrogen peroxide was used. So that makes it oxidative workup. But that's not the case for this. This stays, the aldehyde stays. All right. So predict the starting materials of the following reactions. How many starting? Oh, yeah, we only have one starting material there. So this is an ozonolysis. Notice that I'm gonna tie the end of this double bond to this one. So I know that from an ozonolysis, that was the case. So I'm gonna put this long double bond there. That's the one I broke in half. And notice that this came from oxidative workup. So then the OH came from the oxygen came from the peroxide. So actually here I'm going to have a hydrogen. So the piece from underneath is going to look like this. So that's going to look like this. Are you following? Now the piece from the top will be a ketone. This is a ketone. So this OH, this carboxylic acid, came from the aldehyde after oxygen insertion, because we're using hydrogen peroxide. And so the ketone is going to look like this, where this is not completely finished. So it's already there. I'm gonna do 1, 2, 3, 4, 5 carbons, and I'm done. That's the product. I mean the reagent or reactant. I mean. Okay. So what is, in your own words, what's the starting material for this alkene that has, after you add Lindlar's catalyst, you put 2 hydrogens on the same side? It's a triple bond with an ethyl group this ethyl group, and you have 1, 2, 3 carbons. I'm gonna flip it so that you can see it from a different view. 3 carbons on that side. That's your starting material. All right. Question I have. Oh, what is the name of this reaction? This is actually catalytic hydrogenation, or simply hydrogenation of alkynes. Questions so far? Or alkyne hydrogenations? This is what my says. Okay, so this one right here, what is the starting material? Let's count the carbons. Count these carbons from carbonyl to carbonyl. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, I see an OH, so this is after oxygen insertion. Came from a double bond with a hydrogen. It's not a carbonyl in this case. So if you're gonna put, and then this one, notice that on this side we have a ketone. So carbon 1 has a methyl group attachment. So if I put a double bond here, I go, that's 2 carbons, 3, 4, 5, 6, 7, 8. My starting material, if this is carbon 1 and this is carbon 8, this will be 2, 3, 4, 5, 6, and 7. I put a methyl group on 1, and 8 is a CH. It's like that because it underwent an oxygen insertion. So you can write out the H if you want, but you don't need it. It looks like that. All right. What's the name of this reaction? Permanganate oxidation. All right, we had 2 more reactions. Notice that this reaction was hot. So this reaction is hot. Different to this one right here. Similar ingredients, but this is at 0 degrees, so this reaction is cold. So the permanganate reaction is sort of like the ozonolysis. It will break the double bond in half and put oxygens. And when it's cold, let's do this one before we do the one in the middle. When it's cold, you stop at the dihydroxylation. This is also a dihydroxylation. So the starting material here will be, you have 1, 2, 3, 4, 5. This is tiny. 6, 7. Yeah, so you have 7. Yeah, 7 carbons. Wow, it doesn't erase. Oh, finally it did. And so notice that both hydroxy groups are up or down. This is also a syn addition. And so your starting material is a 7-member ring. How do you make a 7-member ring? So I'll show you how I make one, if I can erase this. All right. So you put like a dot, 3 dots on the top, and 4 dots on the bottom, like if it was a little bolt. 1, 2, 3, 4. So connect the dots, and there you have it, a 7-member ring, where 1 and 2 will be here, and therefore there will be a double bond there and a methyl group. I'm gonna put the double bond inside, it looks better. All right, so what is this next reaction? This reaction is a carbene formation. Reaction, carbene formation. But what kind of carbene? So this is the one you used, this one right here, where you use a strong base and chloroform or bromoform, and you made the carbene. One of the easiest ones to remember, because if you have a base, you will always have a base. Usually sodium hydroxide. Sodium hydroxide takes this H, kicks 1 chlorine, and now you made your intermediate is this carbene. That's what's going to attack, and it does a double slap mechanism. Wait, the double bond attacks first, and then the carbene attacks second. So carbene, so you will have 2, you'll have 1 up or 1, the carbene, the cyclopropane group will be up, pushing the methyl down, or it will be down, pushing the methyl up. So 6, I see a 6-member ring with a double bond and a methyl group, and that's it. All right. I did have enough material for this class. I didn't know this was gonna take long. But now you can take, if we don't have time to do the next worksheet, 6B, you can use that to practice. Now you have a free quiz right there to practice. And I'll be posting the key later so you can use it up towards your advantage.
Can it be multiple choice, or are we gonna have to draw anything?
It will be multiple choice, yes. Okay. But you will definitely have to draw stuff.
I meant like, on mastering where you have to draw it on the screen.
Oh, no. I think the most I could do would be to, like, you take a picture and upload that. Maybe even ask you to do a mechanism and you can upload a picture. That we could do, but it will have to be drawn on a paper. Okay. Yeah, but just kind of multiple choice. I think it's easier, it's cleaner, and we'll go straight to the answers. But even though this looks like something that you would do on a paper test, which this was a paper test question, you still will have to draw stuff. And even if you have multiple choices, I recommend that you draw on a piece of paper to find your answer. Do not try to solve the problems with your eyes only. All right, let's do a few of this, and then you can finish up the rest. Who wants a shot at the first one? What is happening? And I have asked these questions to previous students, so you should be able to answer all of this. Even though you say, what the heck is D? Well, that's deuterium. That's a isotope of hydrogen. So what would be the reagents that you need for this reaction? Notice that from 1 to 3, I ask for the reagents. From 4 to 6, I'll ask for the starting materials or reagents, reactants. And from 7 to 10, I'll ask for the products. All right. What is this happening here? What is the name of this reaction to start? Anybody wants to guess? Who wants to guess this? We have 4 minutes. All right. What does the OH at the end on the least substituted carbon mean? That means hydroboration. All right. So I help you with the name of the reaction. Now you help me with the starting materials. What starting materials are good for hydroboration in this case? I think what is throwing you off right now is that D, right?
Yeah, I was going to ask what that D is.
Yeah, that's deuterium. It's an isotope of hydrogen. Hydrogen has 2 isotopes. One is deuterium and the other one is tritium. With deuterium is with what people build the atomic bomb. It's called heavy water. So the normal water is like this. Heavy water is like this. You have 2 deuteriums. And super heavy water is tritium. Tritium is very hard to find. I forgot the percentages. The percentages are really, really bad. Like if this is like, I'm just gonna make it up, okay? If this is when we drink water, this might be like 99%, and this would be like 0.9%, and this would be 0.01%, something like that. Does that make? No, this one will be like this. So you have to distill tons and tons amounts of water just to get this, just to isolate this. Millions of gallons of water are distilled, and that's what they were doing. The Germans wanted to build the atomic bomb before the Allies, so they had a heavy water plant in Norway that they took by force. And so my boy, what was his name? Start with an H. Heisenberg. Heisenberg was the chemist that was working on this for Germany. He wanted to build the first atomic bomb, but the Allies destroyed that plant in Norway, and so thank God that happened. And so they still did distill a bunch of deuterated water. So deuterium is hydrogen, but it's heavy hydrogen. So yeah, you will need BD3 in the presence of THF and hydrogen peroxide in the presence of sodium hydroxide to do the second step. So that's how you're gonna be doing this. All right, you have another 9 to practice. You can practice. I will post the key for this later on tonight after I finish my 1 o'clock class. All right, I'm going to stop the recording here, and I will answer any questions that you might have.